Yeah, thanks, Kevin, and to all the organizers for having me here and invite me to the last question from the talk before. That's actually, for those of you who don't know that this exists, is the ImageJ user guide. You can get this from the ImageJ homepage, which is actually, I think, 150 pages heavy and has a lot of information on all the functions which are in the basic ImageJ inside. So this helps you already a lot. So if you're once through that, potentially, then you have a little less questions or so to be asked on the user list, which anyway is also a very helpful source. So to this talk, we are going to go through a few things Ari has in overview already presented, especially talking about some processing steps, some feature extraction, so talking about segmentation and analysis using specific functions from the BioVoxel toolbox. That doesn't mean that you can not do similar things also with normal functions from ImageJ. Just here, like, a little bit boiled down. So let's see if that works. So first of all, I'd like to introduce myself a little bit. So what actually is BioVoxel? Because then people always ask me, so where is this coming from? What is this? So far, it's actually me. So the child needed to have a name, and BioVoxel came up because by education I am a biologist, so I'm also not really an IT guy. Exists since 2012, and the main part of my work is actually doing things like this. Is workshops about image processing, not necessarily based or not necessarily only true for ImageJ and Fiji, but generally things you need to take care of. Those workshops are normally around 2 to 3 days. So you see already, as Ari said, this is like things for a whole semester. We actually need more time to go through in detail. That's also why I will only give a glance on a few things here. So those courses also deal mostly with microscopic images, so are designed for natural and life sciences, and have also some part which I think is important to mention in general, because they also talk about image-related ethics, because when you publish in journals, when you publish your images, there are some criteria. Unfortunately, journals often also don't really put clean or clear criteria what they want to have or need to have, but I think there is some general ethics we should stick to not alter what we show too much. And in addition, I'll offer also some customized programming for analysis based on Fiji. So what are we going to do? Just that you get an overview of those who still want to decide, okay, I want to rather slip out and switch to the other talk. So we are talking shortly about some background subtraction and enhancement, then image filters, a few things in detail Ari has introduced already. Then we come to automatic thresholds, so the extraction process actually of the objects of interest you have in your image. Then how can we modulate, so those modifications Ari also mentioned, binary modifications, how can you modulate what you have extracted, and then different possibilities of analyses. In general, I think, so if you have questions or if I'm too fast, please tell me, stop me. I'll try to not rush through, but 2 hours are not so much. So if you have specific questions on how something works, potentially write it down, come up to me later on, and then we can talk about that. So what is actually this toolbox? This toolbox is simply a collection of plugins and macros, which should facilitate some processing and analysis methods, and you see that here. I hope it was not too complicated to install that for those who've done it beforehand, which you can find on www.biovoxel.de or com. Or if you use Fiji, which is my recommendation, is then you simply can switch on the BioVoxel update site and simply update to that newest version. So as you see here, we have some binary operations, binary analysis tools, tools to compare different image filters and thresholds. It also offers some image filters in addition. some background correction things, some line plots, which I also need to update due to this function Wayne introduced in the morning, that we can now zoom in into plots and things like that. So some of this is still not up to date, so this is coming up. And if I have time, I will also show you a few functions talking about particle neighbors and clusters. So this is our workflow progress we want to go through. We normally start off with an original image, so sorry for a biological example here. I know not everybody of you might come from that field, but in principle you can transfer that to all other things similarly, and we first talk about that one and then go through this workflow. So background is not an easy topic in general. RA already showed you the subtract background function, which I'll mention shortly as well, and which is very nice, but we need to be careful what we subtract and what we do not subtract, that we don't eliminate the features of interest, and therefore some things to that. In general, background by definition is rather defined as what you see here. So it's a high offset, a high black level, black noise. And in theory, what we could do here is we could just make an ROI, a region of interest selection, measure the intensity in there and subtract it from the image. For example, under process, image, process and math, and subtract an image state. The problem with that is just that this is the ideal case, and normally what we do not have is a very equal lighting. So if you have, in addition to that, also unequal lighting occurring, then that is already not working. And then functions like subtract background are actually very well handy for that, and that is why we will also go through that. If you have things like that, which is rather unspecific staining or so, which for an extraction later on is hindering your extraction of those spots, some things we will do, then obviously a subtraction of a fixed intensity value is not working, because everywhere in the image there are different intensities, so we need to make a fitted background, which those two functions we'll talk about do, and we can also correct these unequal lighting. Also, this is what we want to go through. So this is one example how the normal subtract background method is actually doing that. So it creates a background here. Again, also this line plot, as you see down here, creates a background from the information which comes from the image, and then subtracts this. And you see that actually outside it subtracts less than inside because of the different intensities you have here. What I often hear also from people is then, yeah, we used that subtract background and then key in numbers until it looks good. I wouldn't do that, because you have seen in Ari's talk that humans can perceive up to like around 60 intensity levels or so. So if you see that it looks good, it might be already too much or too little. So therefore, what you key in here as a radius of this rolling ball tool should be rather based on an estimation of your features here. So how big is your feature size? This is for circular objects very easy. You just make a circle around it. If we have the time, I'll do that later on shortly. Make a circle around it, get the diameter of the circle, and can key that in. Then at least you have a less user-biased estimate. For elongated things like what we have here, like stained mitochondria or so, then it's potentially recommendable to look for the width of the objects, which is a little bit more difficult if you have variable object width, so things getting bigger and smaller. Then we would need to look for rather the bigger areas here, or clumps of those objects. But you see it nicely subtracts a variable background from the image, which makes the processing later on and potentially visualization easier or better. The standard, just to mention that also, you will see that later on, the standard subtract background rolling ball method has a slight problem regarding edge artifacts. You will see that. The alternative is the sliding parabola that actually has a lower tendency for those kind of artifacts. That is a little bit better, but also subtracts a little bit lower background. So this is now a comparison to the first function we talk about in the BioVoxel toolbox. This is the original, just shown in a different LUT, the IC80 LUT, so that we see for the objects of interest better. These are here, these yellow things. and we have the background in between, which is this rather dark bluish part. So if we subtract the background here now with a rolling ball radius of 20, which is based on the size of those features, then you see we nicely can push down the background a little bit. And this is actually how the background image looks like. And there you see these edge or block artifacts which occur. So that is especially at the borders of images is a problem, or for bigger features. So careful with those kind of stuff. So the toolbox now offers a possibility to do very similar things where we can use 3 different functions. So this is actually based on these image filters already mentioned. So the background is created by taking the original image and then filtering it with either a Gaussian blurring filter, a median filter, or a mean filter. Normally the particle size is also actually a good estimate to start with. And if you key that in, there is a preview function, as you see there, or you will see later on potentially. Then if you click on this preview function, you will directly see your original with the background subtracted. And in comparison to that one, you see that at least for those 2 ones, and also actually also for this one, the background subtraction is stronger. But also here, the particle is slightly affected, so we need to be careful. But nevertheless, if we want to work out those spots from the image later on by segmentation, we might be able to separate them better or have them individually better when we try one of those functions here. Here is again a comparison. So basically this would be here the spots, while this in between is actually real staining. In that moment when I want to extract the spots, for me that is background. So this is, as already said, in the eye of the observer. So here I would actually get a lower background subtraction than here, so the particles are visible better and separated better. You see that in between, the blue line is from here, the red line is from this median background subtraction, and it pushes the background in between the particles down a little bit stronger. So for those who have downloaded the zip file, we can actually, if you want to, you can do that together with me or just watch. What we can basically try is one of those functions. I'll do that here with Fiji. And this is exercise 1. You see that up here. Yeah, we can actually use only, for example, the red image. So I'll duplicate that. You can easily duplicate an image by pressing Shift and D. This is the function which is under Image and Duplicate. That is a very quick option to do that. So, and then basically, as mentioned, what I would do here, if I want to work out those spots clearer, the biggest spot is here, this up here, this part. So to estimate the diameter of that, what I would use is normally a roundish tool. Zoom in a little bit. And then create a perfect circle around that object and get the diameter from the circle. So you can get a perfect circle if you not only make with the circular tool a selection, when you press the shift key, while you do that, then you always get a perfect circle. So if you do that and position the circle approximately around that this feature is inside, and then move, so you can take out the mouse and then move actually the selection with the arrow keys of your keyboard up or down, no matter in which direction. You normally see for an image which has only pixels, not micrometers or something like that, there you need to do it slightly different. There you get up here actually, if I move that, then you get up here the position in X and Y, and you get W and H, which is the width and the height of the selection. So for the perfect circle is our diameter. So this is approximately then the size of the biggest feature. And this is the rule of thumb, which is mentioned also in the MHJ user guide. We should use at least double the size from what we get here. So for the radius, this would be then exactly what we measured. So the diameter of that we put in as the radius of our rolling ball is one option, and the rolling ball is under process, subtract background, process subtract background. So if I would measure here 20 and key that in, and then with the preview option, you directly see that potentially better on your screen, how much we push the background down, even though it's very variable inside the image, is one possibility. Now we'll have a look on that biovoxel toolbox function. First of all, where can you find the biovoxel toolbox? If you have your Fiji or ImageJ set up like that and installed the toolbox, then under this double arrow here, the more tools option, there is one entry, which is the biovoxel toolbox. And if you click on that, you get this green little cube here. And from here, you can choose the functions we need now. So if you click on that menu, you will find here, so it's now not in the order we use it. You find here the convoluted background subtraction method. And if you start that, you will get, I hope I selected the correct image. No, obviously not. So first you need to select the correct image, then start convoluted background subtraction. So, and then you see if I, for example, use now the same size I measured and use the Gaussian filter, click on preview, you directly see also how it subtracts the image. Now you can, if you did it beforehand, here you can compare that. That is already subtracting more than the subtract background would do. And then you see if we switch to other methods like the median, does it especially in between the features stronger, and the mean as well. But the mean also, if you look, for example, at the brightest spot here, in this case, the Gaussian keeps it in an intensity which you have here as well, and the mean pushes that a little bit lower. So you also need to be careful that you do not lose low intensity objects in your image. And when you press OK, then you apply that to the image. So this is one option to basically push the background down before any extraction. If in addition, or especially for those kind of images, when I can try that later on, when you have images like that, so if you have an image which is phase contrast or DIC or anything like that, then the subtract background option is not working. I'll show you that later on, because the problem with that is it creates specifically artifacts, because in such an image you can hardly define any object size. So what we do there, or what we can do there, is get either an imaged background. This is the optimum. So if you directly, before you do your imaging, you take one image without any sample, just in the lighting conditions you have. If your microscope still, even after setting it up correctly, still has any problem with the lighting, what this function actually does is it uses that background image and divides the original by that background image. So you can imagine wherever you have dark areas, so low values, and bright areas, so high values, you divide low values by a lower value and high values by a higher value. This means basically what you do is you level that on a similar level. But if you imagine this is a gray value of 100 and you divide it by 98, you get 1 point something. So you have an image which is almost black. And that we get back into the original intensity scale, we multiply what comes out of this quotient. We simply multiply each pixel with the average intensity of the original image. And then we get back to an image which is actually corrected for here. So what happens now if you do not have such an image in the first place, or you haven't taken it, yeah?
What is the difference between this and subtracting the background and adding the mean?
Because if you subtract, so the question was, what is the difference if I do a division or if I do a subtraction? The difference is simply that if I do a subtraction and some value is here the same or higher, then I get below 0, so I have black, and then I can multiply it with whatever I want to. If I multiply 0 with something, I get 0. So I will never get it back into basically the original intensity. I will still keep it black. And with the division, that is not happening. You always stay above 0, basically.
Use a floating point. I mean, subtract and add the mean.
Yeah, with a floating point, it should be possible. Need to think about that. Yeah, that's true. In this case, we use the division, and as mentioned, if you do not have such a background image taken, we can create artificially one which is not optimal, but we can try to do so. This might not work for all kind of images. For those kind of images where you do not have a very, very strong contrast, it most likely will work. In this case, this is done again by applying an image filter, so a strong Gaussian blurring. There are other methods, as already mentioned, where you can also specify specific points in the background and the computer creates you some kind of fitted background. This is the second possibility. Here we have only the filtered image. So this is how it looks like. In this example, we will do it with the same one. You see in the line plot, if I make a line and plot it over from bright to dark, basically here you see the clear tendency that the intensity drops, and after the correction, this tendency is corrected kind of almost completely, while all the features are still visible. Actually, I forgot to mention, I'm sorry that my slides are still not up online, but I will do that because I changed them until yesterday, so basically you will have them after the workshop here available. So if you want to test that, if you go to the images and that files you could download of exercise 2, there is one option, one image, which is here first, unequal lighting, DIC. So that's the first one we will have a look at. Which shows this difference. So now if I use this subtract background function, just to show you that quickly in the preview, no matter, first of all, I can't define any size of any kind of feature. So when if I use that, then you see that it actually creates artifacts. So that I can't use that. And my problem is actually rather that I have this unequal lighting. So the subtract background is nice for fluorescent images or anything which gives you bright signal on a dark or black background. Here we would use the other option. Under the green cube, you will find two possibilities. Flat field correction means you have a background image, which you can use to simply divide the original by. I'll just show you that shortly. We are not using that. So you need to specify the two different images, original and background. The option we need to use now is actually the pseudo flat field correction. Pseudo because we create a pseudo background, which has the problem that it comes from an image which has information. So that's why it's not optimal, but it's a possibility. And then you see that you are actually asked for a blurring function. So far the problem is that the background mostly comes up where this one is located. So a blurring radius, and the default value is 50. That doesn't mean that it's good, that's just any default value, and you need to test it. How can you test it? That's why you have a preview. If you go to preview, you see a background image, and the importance in the background image to look at is that in this background image, you do not see any kind of features which were present in the original image. Because you see now already, this is potentially what you haven't noticed so far. Preview, if you switch that on and off, you see beforehand and after the correction. So you see the correction directly. So now the problem is if I use a radius here which is too small, let's say 5, then you see in my background image I still have information from my original which is taken to divide the original by, and that obviously is counterproductive because then I destroy my image. So that means I need to go up here, and there is not the optimal value, there is a potential range which makes sense to use. So something here between 40 and 60 is fairly well suitable, but the bigger is not the better, because if I now go, for example, to 500, then you see that actually now I have again my different lighting. It's just slightly corrected. And the reason for that is that if I blur my background that strong, then I eliminate completely also the shading differences in my background. So obviously I have nothing to correct by. So that's why this is not really helpful. So you need to find a value where you don't see any original information anymore, and then can apply that to the image. And if you want to, you can store the background image to have some proof how you corrected it. And then we see, if I make that plot, so I draw a line and then go to Analyze Plot Profile. So this is now live. So this is before, and this is after. So this is something which is also helpful not only for those kind of images. I'll just show you that quickly in the same exercise is also fluorescent image, because for feature extraction we often might have the problem that in an image some features are naturally bright because they have a lot of fluorescent information or material, and some others are dark. So now if I want to extract those spots from all those three objects here, I'm kind of lost, because with the same threshold I will not get them out. So just to show you that here shortly, if I would threshold them, I get either some of the spots here, then I get here too much, or I get it from here and then I lose all the other ones. So that is not what I can, so like this I can't process the image directly. So what we can use this function I have shown you for is also to actually level these different intensities to a similar or the same level, which later on will help us for the extraction. So we actually misuse it. So when you go to the green cube and use again the pseudo flat field correction here, in this case 50 is a little bit too low, the radius, but we can test it. So I mean, see here, if we go to 80, then it blurs that a little bit stronger. So, and then you see actually beforehand they were different, and if I activate the preview, then you see they are very similar. So now you can't use those images obviously anymore for any kind of measurements, that's clear, but it should help to push that into the same intensity. So obviously now I have a low contrast. If I then in addition enhance, for example, the contrast or a little bit more, then I'm basically set up at a point where I can start doing further filtering and then the extraction, for example. So this is a possibility how this can be applied as well. So besides those functions, enhancing the contrast, subtracting the background, we often also need to think about filtering our images before we want to extract them, because that might make things clearer, better visible, or actually eliminate things we don't want to extract. I don't want to go into details explaining the filters. Ari has done that actually very well already. Just to show you where can you find them again. Process filters, there are the basic filters for 2-dimensional and the same ones for 3-dimensional images. In general, we use them normally to either denoise the image or blur structures. You have seen one example where we can use the Gaussian blur to blur some structures. Or homogenize intensities. This is something which later on will become very important, because whatever looks more homogeneous is clearly visible for a human eye. This belongs together, and then also for a computer it's easier to decide, okay, these pixels belong together and should be extracted together. We can also use to sharpen images. Ari has shown this sharpen function. There is actually one for those kind of images which is slightly better. This is the unsharp mask here, because the sharpening function has the problem that it sharpens around every pixel, and if you have noise, it also pushes up the noise. The unsharp mask does this a little bit, does not push up the noise too strong, because it specifically enhances around edges, so that has an advantage. So it's actually a good option to look at the unsharp masking in the manual, and also testing that on images. So we do that for feature extraction later on. Important is now that what I want to show you is that we have in the Biovoxel toolbox a filter check. This should be there for comparing different filters, because you've seen that what we have is we have Gaussian, median, mean, and we have some other filters, including statistical filtering. And in this case, the filter check should enable you to have them next to each other, and then basically also go through the different versions of the filters, because you've seen normally what we do is when we filter, we key in a radius. This is for our filter size. The bigger the filter, the more it normally convolutes or blurs the image. In that case here, you see that we have two radii. We need to key in a starting and a stop radius. That means that image.j will, or feature will show you then later on a stack, and every slice has the first one as the original, and every slice after that uses one step more of the radius, so it gives you basically an option to zoom through higher or lower filtering of the image and compare that to find best the filter options you might want to use afterwards. The parameter function is ignored by all filters which only use a radius. Some filters, like the mentioned unsharp mask, actually need a weight function, and this is then when the parameter comes into the game, but normally for the standard filters you don't need the parameter. Only mean shift and unsharp mask, for example, uses the parameter. So we can test that. In exercise 3, I think we test only the first, because this is also what we want to analyze later on. We only test the first few filters. So if you go now, having the original active, clicking on the toolbox and going to the option filter check, then we simply test first the Gaussian blur. Start with a radius of 1 and do it up to a radius of 10. Mostly you don't need such high radii, but just to show you the comparison. The parameter is not necessary here, so we ignore that. So if I press OK, I will get a stack. And you see if you go through that stack here with the mouse wheel or the slider that you have this increasing filter options. And this is actually indicated up here. So the radius, you see which radius is this slide which is shown and which parameter was used in addition. So we can do 3 other filters here. So we go back to the original, then to the filter check. And then we use the next one, which is the median filter. Also 1 to 10 to have a better comparison. And press OK. So in the last one, I'll go back to the original green cube filter check. So we skip the Gaussian weighted median that has a long computation time. I'll show you that later on. We go to the mean. And also here, 1 to 10. So, and by just looking at them next to each other, so for example, if we go at a radius of around 8 or so, then you directly see the difference. The Gaussian blur obviously does a strong blurring in the way how it works, because it gives a weight to the filter and multiplies the values. So that's why you actually get a very strong blurring. That is something which might be very helpful if you have a very noisy image and you only need to later on extract features in a way that you want to count spots. So you just want to recognize bright spots somewhere, then it might be helpful. But if your interest is actually you want to extract objects of interest in a way that you later on want to measure them by size or anything, or you want to use them to create ROIs from their outline to transfer it to a different image, then obviously that is counterproductive because the extraction will be either smaller or bigger. I can show you that later on. And the mean in comparison, you see that if I go a little bit lower, for example, to 5 in all 3, the mean actually is somewhere in between those two, but it keeps differences a little bit stronger. So the Gaussian reduces noise stronger than the mean, and the median actually also, spot noise is eliminated very well here. The mean keeps those bright spots a little bit longer. So just to show you a comparison of the object size between those two, I'll make a line somewhere over a few of those cells or nuclei. I put that to the ROI manager to transfer that later on at the same position to the other image. The ROI manager, you can simply use T, which adds that to the ROI manager. And then what we can do is with this line, we can simply make a plot profile under Analyze Plot Profile or simply press K. So now if we go to the other image here and click on the entry in the ROI manager, this line is transferred to exactly the same slide in the same position. So and here, if we go to Analyze Plot Profile, we get this one. So you see it's slightly different. So and potentially that makes a little bit clear what the problem later on is. We extract our objects with a threshold. The threshold is simply an intensity value at which the image is divided into interesting, not interesting. So the problem is if I would just indicate here a cutoff, which I would use, and then you imagine that this cutoff value is higher or lower, then you see in this object what I extract. If I do it here, my object, just to indicate that, if I would do it at this level, my object would have that size. And if I do it at this level, my object is smaller. So in the median filtered case, this is not as strong because if I do it here or if I do it here, you see that the final object size is very similar. That is why the median filter preserves outlines, preserves edges, and preserves sizes of objects better and is actually more suitable for those kind of purposes to extract that. And that is also why the filter check should help you in these comparisons to basically see, okay, I'm going up to a point where I eliminate those bright spots if I don't want to have them anymore. But then I also should stop because you also see a second problem at some point which comes up if you look at this encircled area here. Because if I now go higher with my filter radius, then you see at some point it also connects the features. And that is obviously often counterproductive. We can counteract that later on with the watershed, but this also only works in some conditions, in some others it doesn't work. So if we directly can keep them apart, it's most likely better than later on fixing the problem we created beforehand. So in that case, what we could use for later on would be something around a radius of 5 that eliminates sufficiently the spots and keeps them separated still as good as possible. So that would be an option actually. So this is what you can keep in mind, because that is basically a point where we would continue later on. There is, in conjunction with that, a second filter which I have mentioned, which is in the toolbox, which is very similar. This has a higher computation time for the way how it works. I will explain that for those who are interested in the next slide. So you see, if I use for this image the median filter, at some point I get them connected. The Gaussian weighted median with the same radius actually keeps them still at this point separated. If we make this dashed line and the line profile, you see that these peaks are actually eliminated. And the gap in between, which is necessary to keep to separate those two objects. Now this is here a problem because this gap is here higher, and here you see it's still lower. So if we use such a cutoff value, then you see what actually was separated stays separated, so we will keep them separated after our extraction. Here it will be connected because our valley, the end of the valley, is actually still above our cutoff value. So in this case, if you see already I need a high filter radius for a median filter, and you see that your objects which are close together get connected, it might be an option to switch to the Gaussian weighted median, but that includes a little bit longer waiting time for the processing. If you want to, you can test that. I think we don't do a separate exercise for that, but you can use the same image now, the original one we had, and can apply the Gaussian weighted median. which is in the toolbox just down here. Gaussian weighted median, and can key in a radius, and then you will see how that actually works if you use the same radius as for the median. So why is that? To also feed those of you who have a little bit more background in those image processing. So the normal Gaussian filter actually uses the values and gets the normal median value, so the statistical median value, by taking those values, sorting them by size, and then taking simply the value which lies in the center of the sequence. That is how it exchanges later on this pixel, which had originally a value of 54, by a new value which is 75. Now, the Gaussian weighted median filter uses, in addition, such a weight matrix. That simply means that what it does is it multiplies the occurrence of those original pixels here. So this one is actually put in 3 times. And that's, you see why it's called Gaussian, because it actually makes a 2-dimensional Gaussian bell curve. And by doing that, when we then sort it, then actually the median value shifts a little bit, and that keeps the focus concentrated on the center of that filter, and has the advantage that edges are preserved the same way as the median, but it keeps the separations for longer. Just so much for that. There is a second filter in which you also can try basically by yourself if you add noise to an image, which is the so-called adaptive filter. The adaptive filter, you see that when you have noise in an image, the median filter, because of the principle Ari explained, that it actually eliminates outliers. The noise is an outlier normally in a homogeneous environment, and if you apply a median filter, you get rid of the noise, of spot noise, especially efficient. So you see that actually here, but you also see in comparison to the original that after a median filter, the pixels are somehow grouped and you get rather a homogeneous or a blurring. So, and if you use an adaptive filter, the adaptive filter modifies that a little bit, because you can specify a tolerance, and the tolerance has the effect that it exchanges only those pixels which are above a certain threshold value. So this means which are has a stronger difference to their surrounding, and keeps the other pixels of the original image. So that's why you change specifically only those pixels which are outliers, and the outcome is a little bit more similar to the original. It's not perfect, nothing is perfect, but it keeps you the original values slightly better. If you want to talk about that in detail, how it works, we can do that also outside at the poster later on. This is also, if you go to the toolbox, here it's the adaptive filter. Potentially, I don't know, time-wise, I'll try to can show you that shortly. So if I have any kind of if I add noise to that image, and then apply a normal under process filters median, a normal median filter with a radius 1, you see the noise is very quickly removed, actually fairly efficient, because it's spot noise of mostly size of 1 pixel. But if you look closely to all those masts things and lines, ropes, then you see that at some point here we get a fusion, so the details are lost a little bit. So, and if I do the same thing, I'll try to put that next to each other here. No. If I try to do the same thing here with the adaptive filter, I also, to compare it, use a radius of 1 and use a median option, because the mean option would be not so good because mean is prone to noise, median is not. For shape, at the moment I take the X shape, that you see what that means, and as a tolerance we can use here like 0.15 or so. That is something you need to try. That's not what you can know beforehand exactly how much you need. So that means if the difference, what it does, the program, is it filters the image with a median of a radius 1, exactly what we did before, and then compares this to the noisy image and exchanges only those pixels which have at least 15% of difference before and after filtering. So X shape comes now. X shape is basically that. That's also why it's called adaptive filter, because you can tell the program use only these pixels for filtering and skip the other ones. And X means simply, as you see, which ones are active. Now we need all of them, so I reactivate them. And if I now press OK, and then look at this area we had beforehand, then you see in comparison to the normal median, we actually keep details a little bit better. So that is one option. Using the adaptive filter might also serve for eliminating lines. If you make the filter perpendicular to the line, a very thin line, a pixel line, you might be able to remove that. So, to continue, now we're coming actually to the little bit more difficult task, which is the extraction of the objects, and especially doing a reliable extraction, which is not always possible and is not always easy. Why are we doing that? Because we can, no matter if we have true color images with different colors or intensity-based images, we can extract colors of interest or intensities of interest and then later on quantify, for example, a positive area. We can quantify colonies or cells and count them later on. We can also analyze, and I'll show you later on an option, analyze things by their shape, as already mentioned, so we can see if something is rather roundish, not so roundish, has a certain angle, and so on. And we can use these extracted images, which are always the white and black and white ones, to create regions of interest and then transfer them back to the original image, which is actually very handy, because if you have hundreds of images with thousands of objects, you don't want to draw rows in all of them. So you can basically automate that with macros and first extract that, create the rows, and then transfer them, as you see later on. So how is this done? The segmentation in its easiest or simplest case is done by a binarization. That means we divide the image in two parts, interesting, non-interesting, or foreground and background. Since we have intensities in our image, and our image with bright objects and a dark background here creates, so you can see that as a landscape. So you have peaks for bright objects, and for the valleys you have, for the dark areas you have the valleys. Here's the intensity range, and now if we flood that landscape, everything which is below the water level is basically what is eliminated and the rest is kept. So the higher the threshold is, the more is eliminated, and then you can imagine that it's extremely crucial to find one cutoff value which gives you an extraction which has not too much false positive, not too much false negative pixels, and that is exactly what is not trivial. Ari's shown that already. We can use the manual thresholds dialog. That is a little bit tedious because first of all you have two sliders for two cutoff values, an upper and a lower one. Then every of those sliders has 256 possibilities. So you have 2 times 256 possibilities. If you take only one, it's already a lot. And the problem is, where do I set my cutoff value? So the first thing is that it's time consuming and it's very biased. Especially also a problem is that when you want to compare images, extractions of images to each other later on, you need to apply exactly the same cutoff values to all of your images. And this is where you actually have a problem, because if you do so, your images have natural variances, and then it's actually not working anymore. Because if you use a cutoff value which is different for every image, then it's somehow not really comparable anymore. So it's not applicable to multiple images, which is often the case. Especially your pre-processing and imaging is perfect, but that is difficult to achieve always. So here are already automatic thresholds, but we will have a look rather on automatic methods. If you want to, you can also have a look at the image from exercise 3 and can start this threshold here under image adjust and threshold, and can try to figure out if you find a threshold which is actually suitable, and you will very quickly figure out that is a very difficult task, because if we pull up that threshold dialog, so either I get my bubbles, then I get a lot of background, or I get rid of the background and then I don't get those features completely. So that's already where I have a problem, at least when I'm working with the original image, and that's when filtering becomes important. So here is similar image, 4 images from the same series in comparison with two fixed values of this manual threshold here. And then you see the third one looks nice. Those 2 ones have a problem, which are the holes, and they have background. Here the features don't have holes, but we have a lot of background. So difficult, because we need to get rid of that one. And since the background is rather spot-like, as Ari mentioned, the background subtraction method is not working because those spots are smaller than our objects, and it will not remove the background. Now if we use an automatic thresholding, then you see that background problem is partially solved already, because every automatic thresholding method is based on the histogram normally, the ones we have here. So it chooses the current histogram of that image where it's looking at, deciding for a cutoff value. So the absolute cutoff value is different for the images, but it's comparable because you use the same algorithm. So you need to use the same auto threshold for all these images, but then it's comparable. So basically what you get here is still you have the holes. We deal with those later on. You will see functions which do that. But the background level is very similar everywhere, so the extraction is slightly better. So, and this is a very nice tool. If I'm not mistaken, it's also initiated by Gabriel Landini, which offers us that here. So we have 16 different methods, and if you go to the Fiji homepage, you will find also the publications listed there. Those are some of them are coming from the 1980s, so it's old stuff, but it's very good. 16 is still a bunch of things, but it has a lower bias because we go down from 256 possibilities to 16. So what can we do? In the beginning, we have no idea which one of the 16 is good. So we can test, this is also a nice option, test all by choosing try all. We need to tell the program still, do we have bright objects on a dark background or the other way around? Activate that here. Additionally, you have a function which says ignore black and whites. Normally, I always skip that in the beginning, and only if I can't find any good threshold, I try it again with one or both of those active. This means simply by defining the cutoff value, it ignores black pixels or white pixels or both, because they influence the histogram, so they also influence the cutoff value. And if you have a lot of them, that makes a difference for some thresholds. So it's an additional option. In the beginning, I would first try it without that. So if you apply that with try all active, then the outcome looks like that. You get a montage with the 16 different output images. And then the question comes up, which one is best? And that is already, again, a little bit troublesome. Here it's clear these two are not so good. For some of the other ones, they are very, very similar. So we need to have a kind of decision making here. And that is again where the toolbox comes in, because the toolbox offers you the same thing. So it uses this auto threshold provided by ImageJ. Then it color codes them in comparison to the original image. And that should help you in making that decision. That's not an absolute tool which tells you use this and you're happy. This just should make it easier. So how is this color coding? How can you interpret this color coding? your features of interest, you see that here after filtering, more homogeneous, are shown in yellow, and if in areas where they are not so bright, in orange. That is basically what we want to have, what we are interested in. If you see red area, that means these are false positive pixels because they are overestimated, so the threshold would extract it, but you don't want to have it. And in that case, when you have something like that, that means you have too much false negative ones which are not found by the threshold, but you want to have them. That means bright blue, false negative, red, false positive. So what we would look for is a threshold which looks like that, and that is actually fairly well. We have still two problems for our later processing. We have connections, we can deal with that. And we have small particles, we can also deal with those ones. At least if the size between what we want to have and what we don't want to have is somewhat different. How is that working? That works very simple. It uses existing methods. It simply takes the original thresholds, all the 16 methods, then applies this high-low LUT already mentioned, where white pixels are red and black pixels are blue. Then it takes the original and applies a green lookup table, and then simply combines these two images, and green and red gives you yellow, and black and red would give you here, the green and the blue would give you this cyan. So basically that is how these are created. So whenever there is an interesting feature which is bright in that image, you should see that here, orange and yellow. Additionally, but I think we skipped that for the workshop because it makes things then too complicated and time intensive, this has also a semi-quantitative option to get a quality measure out of that. This is also not perfect because it's based on a selection by the user, so you need to identify a point in the image where you say, I still want to have that after the thresholding. So if you have bright features, there are some dark areas which you are still interested in, then you can put a reference point there. And according to that, the program does a quality measurement comparing true positive versus false positive and false negative and gives you a quality output, and thereby suggesting you a threshold which is best. But that obviously massively depends on where you set the reference point. So this is what we can test now here. We use the same image we had before from exercise 3, so this one. Let me close the other one. Okay. So, and then if you go to the green cube and choose the threshold check, then you see here exactly the same possibilities or options. You have bright objects on a dark background. That is what we have. So we would choose that one. Honestly, I'm incorrect. Sorry for that. We obviously need this one. So do you still have that open? If not, then take the original. Go to Process, Exercise 3, the image. Go to Process, Filters, Median. That was what we did here. And this was done with a radius of 5, which gave us a fairly good outcome. And then we should see the same here and apply that. So we continue working with this individual image. If you have still the stack, then please duplicate that image out. You can simply do that from the stack by running image duplicate and tell the program, no, I don't want to have the complete stack. I only want to have this image. So if this is not active, you will simply get a copy of the active image out of the stack. So this is where we are. In addition, what might be helpful is having a higher contrast. All these convolution filters always reduce the contrast in your image, and having a higher contrast might make it easier to find several thresholds which are working. So what we can do is still we can enhance the contrast, and one function for those kind of things which is very helpful is under Process, Enhance Contrast, because it does it automatically. makes different images a little bit more similar. So it's easier and quicker than using those manual sliders in the normal contrast and brightness settings. So what we don't want is we do not want to saturate pixels, otherwise our background comes up if we do so. And what we want to do is a normalization that is simply applying the normal contrast stretch to an image, as Ari has explained. So process, enhance contrast, and then select no saturated pixels, so 0, and normalize. So if you apply that, you see that the contrast is set up a little bit, increased a little bit to the maximum, avoiding any kind of oversaturation. So, and now, from here, we start the threshold check. So, green cube and threshold check. As mentioned, we have bright objects on a dark background, so that should be active. We don't use ignore black and white. The middle part is interesting for local thresholds. That's getting more complicated. In most cases, that's also often not so helpful because it extracts in addition a lot of the background. You can have a look at that, so if you want to, you can switch it on. But it's difficult to find suitable parameters, so again, the user bias is increasing. So I would try first the global ones. What some of those functions are good for, I'll explain you that one later on. First of all, we run it like you see it here. So, and if you do that, then you will get a stack. You could have also chosen optionally a montage where you see them next to each other. It's another possibility that's up to you how you can compare it better. You see the thresholding method mentioned up here, and then we can go through and can have a look which might, based on a visual perception, be the best extraction. So we see here that is definitely we would lose much of the information because everything which is bright blue is lost. And this one would be definitely too much, so everything which is red is extracted, but we don't want to have it. So, for example, default doesn't look bad, but if you look closely, then it's actually telling you, okay, here there is a complete nucleus, and here as well, and we don't get that completely. So that is already not the best one, even so in the beginning it looks good. Here, it's better, we get them completely, but we also get additional things, so potentially should have a look further. And in this range, when you go through, actually the best one, if you use the median filter of 4, the best one is the Renyi entropy, because it has all the outlines, it has smaller connections than the other ones, and it has not so much of those unwanted particles in addition. So based on that, I would choose that one. You see the connections. We need to deal with that because we want to have our particles individually. So how can we do that? We can directly test it with the threshold check. If we use a specific threshold, can I then still separate my particles afterwards with using the normal watershed function? So this means I run this again, so I close that. And then important is, otherwise some of you might get artifacts in that, it's important that we define that we use a black background in the binary image and white particles. And you can do that under process, since we are working on binary images then later on, binary, and the options. That is actually an important panel to check. If you go to process, binary and options, to check that your black background option is active. That should be active now, because otherwise for the following function you will get lines in between the cells. So now if we run green cube, the threshold check again, bright objects, and now in addition what I will switch on is test watershed ability, which should show us if we can separate them afterwards. If I now run that, pressing OK, you see it looks the same. But if we go through, then you see that actually now, which was not the case beforehand, between those objects we have blue lines, which is background, blue is background, so that is basically cut up part here, which uses the normal watershed function. So this tells you, okay, if I use the threshold Lie later on, then I can still separate the particles exactly where I want to separate them. And since I decided beforehand Renyi entropy looks actually best, we can have a look at that. And then we see, okay, these ones were connected, are separated, these ones as well, and even the small piece I can cut off still. So actually Renyi entropy would be finally a good choice. So if I have made this choice, this is just the decision-making process. Then I still need to apply it to the image. So I go back to my original, or my filtered processed image, and use the standard function. So I go to image, adjust, and auto threshold. And careful, because the threshold check uses this auto thresholds. In this manual thresholding dialog, where you have access to the auto thresholds as well, there are some differences to this auto threshold, so you need to be careful that you use the auto thresholds. Image adjust auto threshold. So we said we want to use Renyi entropy. So I choose that. The rest needs to be the same as beforehand, so no black and white objects. And now you see if I press OK, I'll get my objects extracted into that binary image, which I can use then later on for the analysis. But you see also that it's still connected, obviously, because we still need to apply this morphological operation. And this is now done, and hopefully better make a duplication of that, because it might go wrong. So go to image, duplicate. Sorry, it was a little bit quick. Image, duplicate. And accept that and continue first with that one. Since we are working with binary images, now we go to process, binary, and the function, what we want to use is watershed. And when you apply that, then you see in comparison, actually, now we get exactly what we've seen beforehand. We get the separation. If anybody gets a strange result, I can reproduce that here quickly, that everybody sees what I mean. If black background would not be active because any plugin or whatever switches it off, if you then go to watershed, then you get something like that. Because now the computer thinks black is interesting and are the particles, and it separates the black particles from each other. So if you see that and you don't want it, then you know, okay, I need to go to process, binary, and switch on the black background. And that is also what Wayne mentioned in the beginning. It's so important in a macro to always specify if you have a black background or not, because otherwise it depends on the settings the user does, and then it works or it doesn't. So now this should work, watershed, and then we could basically continue with our analysis. Before we do that, still a few explanations on that. Because here we have already the particles we want, but sometimes we might need to modify things. So watershed is one modification. There are other ones you might need to apply. For example, some basic standard functions from ImageJ, what you might have because of different intensities after an extraction, you might have holes in your features. So if you want to measure the size of those features, the whole area is subtracted from the full area, so it's not an option to do that. So the simple function would be under process binary to go to fill holes, which will close the holes. Careful, the characteristic of a hole is that it's included in the particle. So that means if there is only a 1 pixel connection to the outside, this is not a hole anymore, this belongs to the outer part. So the function cannot identify it as a hole and will not fill it. Then we need to do it slightly different. The watershed you have seen, and that the watershed has some limitations you will also see later on. Two other functions Ari has explained already, so just shortly, we have erosion and dilation, so we can make things bigger or smaller by shedding off particles or adding them, and we can combine these functions. This is then open and closing, where we do first an erosion, then a dilation, or the other way around. First to these ones. if we use the standard function and we need to use it only like with one pixel row, it's not a problem. It just takes off one pixel row and everything is fine. But if our processing requests us to use that more often, then you see here, if I do that 40 times, so for this is my original particle, and if I do that 40 times, either an erosion, a dilation, or an opening closing function, then you see here you get these lines and here you get these blocks. So the original shape is altered. And that is why when I introduce here the function from the toolbox, which is called EDM binary operations, it has exactly the same options here with the nice radio buttons Wayne mentioned in the morning. So we have the option to choose one of those four, and then you see actually this is based on the so-called Euclidean distance map, so which is a transform which shows the distance from the pixels of your object to the background. And based on that, we can keep the shape a little bit better if we use those functions. So if we need to use higher numbers, iteration numbers of dilations, erosions, opening, closing, we can actually preserve the shape better, avoid these block artifacts because it's more isotropic. Before we do that, additionally, the explanation for the watershed. So the watershed is a very nice function as soon as you have like elliptical or oval things which are connected by a thin connection, then it works perfectly. But what if you have these kind of amorphous objects? Then it is troublesome, because if I apply the normal watershed, then I get this one. So I have actually 5 objects, and after my watershed I have several ones, so I over-fragment those particles. This is what I obviously want to avoid. And therefore, we have a second possibility, which is called watershed irregular features, that has so far 2 options, thanks to Thorsten Wagner, who added the convexity, who is also here at the conference. We have 2 possibilities. So you can do it either by an erosion cycle or by a convexity. The next slide shows you what the erosion cycle does, and potentially it gets a little bit clearer what is the function. So, and you see that now, depending on what you key in, we can separate those ones by not over-fragmenting them. So you cannot get more separations than in the watershed, but you can get less separations. And the convexity is simply a second opportunity. If you key something in for the convexity, it ignores the first option of the erosion, so either or. I don't want to confuse you, but that is basically on how it works. It takes the original images, and in the background it makes 2 things. It takes one image where it does the normal watershed, and it does one image where it does an erosion as often as you key in the erosion cycle here. So that means the erosion makes the particles smaller, and then it compares these 2, it first extracts those separation lines by comparing original and separated ones. And then it compares these 2 and says, okay, if those separation lines are still lying in an area where there is a particle still, then I don't want to separate that. But if there is an area in between where there is no particle anymore, then use it and separate it. And that is basically what it does. Then it separates it only here. And the erosion cycle does it similar. It just first selects only particles in the image which have a certain higher convexity, and then does a one-time erosion and does this as often as there are particles with a higher convexity than that. So it's similar, but you can get different outputs, and sometimes one or the other works better. There will be after the workshop also an update and some time where I will add also a possibility where you can choose the length of the separation, so you can specifically tell I want to separate only where the separation line has so and so many pixels, which lets you modulate that in a better way. So we can test first the erosion. Exercise 4. Therefore, we first take these 2 ones, nuclei binary and nuclei original. original just to show you how the original looked like and the binary after the extraction. A suboptimal extraction, obviously, with holes, we have those features not complete. So different possibilities. First of all, I have connections here. Now, if I directly want to try to separate those connections, that will go very wrong. So if I go to the process, binary, and the watershed, then I get that. So I cut everything in pieces. That's obviously not an option because I still have too many holes. If I open this binary image again, so the holes were the problem. So if I first fill the holes, process, binary, fill holes, looks better. Not perfect here, but better. If I then do the watershed, process, binary, watershed. So here, nice, here, nice, not so nice, also counterproductive, and here obviously as well, and I still don't have them complete. So this is a better, but not the optimal. So I'll open the binary again. Now you have seen we have this closing and opening function where we can also deal with those kind of hole things. So first, I'll do that here on a copy with the normal image J function. This means I go to process binary, and you see them listed here already, but that does it only as it is set in the options, so it does it normally now one time. And I want to have it more module, so I go to binary and options, and then you see under these options, I can here choose if I want erode, delete, open, close. So first of all, what I want to do is I want to close the holes. And here is the iteration number, so I can choose how often I want to do that. So let's say if I go to preview, then you see if I do that one time, it does already to some extent. And if I do that 5 times, then you see that they're actually nicely closed. And this two at the side here are actually also rather, so have a better completeness than beforehand. But you see also already that we get slightly these connections to smaller particles, and at some points you have the feeling that it's like blocky a little bit. So another or what comes next is I need to still separate them and also get them a little bit more roundish. So now what I've done is I have done a closing, now I do the opposite. I do an opening function. So I go to process, binary, options, choose open. And then if I go on preview, you see with 5 iterations, it at least nicely removes whatever is at particles in the background. I still have those connections. If I actually go a little bit higher, not really. Yeah, now with 12 or 15, then you see now these are at least separated, but now it gets like very, very blocky. So we can keep that for now first. We'll do that like, 12 or 15 times and accept that. So if I create a selection from that here by going to edit, selection, create selection, just to show you that on the original, I get selections around those objects, and if I go then to the original and project them with Shift E, then you see this is not so nice. So what is the alternative? I will save this here in the Roy manager that later on we can compare that. The alternative would be, so transferring selection is Shift E transfers selections. So not transfers, it actually gets the last selection back, but if you're in a different image, you transfer that. So if I take the binary image again, and now you do the same functions, but do it with the toolbox. So I'll take that image, go to the toolbox, and use now the EDM-based binary operations. What we first did was we did an opening. We can also click our way through those ones. If I go to preview, you see erode, delete, open, close. First we did the closing. So we did it 5 times. And then you see here, it does very similar. So closes that, creates connections, but keeps the outlines already a little bit more roundish. So I accept that first. 5 times iteration, close. And then I do again the same function, Toolbox, EDM binary operations. I'll go to open, and I did it, I don't remember, 12 times or so. So, and then you see, I'll have them roundish. Actually, can go to 15 or 20. Then I have this also separated directly, and it does not alter the shape too much. So you see in comparison, and here I keep the shape, and if I create a selection from that one, selection, put it to the ROI manager, and we can compare that on the original. This was the first option, and this is the next option, and then you see that it's actually nicely fitted. Actually, I forgot the watershed, so in this case, what we still would need to do is separate those connected ones, and that is here nicely working with the standard watershed without separating any others. So we could create a selection here with separated particles and nicely fit ROIs. So much for this modifications of binary images if necessary, which is not always the case, but if so, you see then where you find that. Now we will rather have an eye on the analyses of those binary images. First of all, what we have as an option here is sometimes what you might have is you might have 2 things. You might have an image with fluorescent marker, for example, marker A and marker B. And you want to see, similar to a co-localization, where is some kind of overlap. That would be a purpose for the following. Or if you want to extract specific objects from the image and work only further with those ones if they coincide with an object in a second image. So therefore we have the binary feature extractor, so you can use that also to get directly an analysis of the objects, but that is rather seldomly the case that you need that. But we can separate them, so you have an object image and you have a selector image, and the selector image decides which objects are kept in the final image if they have a certain overlap. This means if you key in 0, it gives you the object as soon as there is a 1 pixel overlap. Otherwise, it checks how much percentage of the selector overlaps with the object, or how much of the object is covered by the selector, actually, and then extracts that. So this is what we will do first, while also having a look at the analyzed particles, and then show you a second possibility for these kind of analyses. So what we need is we can actually close all those images, file, close all. And go to exercise 5. So we can open those 3 images here. This is the one you've seen beforehand already, but now extracted. So I extracted 2 things, the spots and the bubbles, because finally it might be interesting, how many spots do I have per my nucleus or whatever. So how many small things per big thing. First of all, what I still need to exclude here is, in those kind of analyses, every object which touches the edge, because it's not complete, that would mess up my results. And all the small things, because they are obviously not objects of interest. So to this end, it might help to estimate what is approximately a size for an exclusion to eliminate the small ones and keep only the big ones. Just quickly, how you could do that would be, there is this nice vent tool, and this vent tool selects, when you click in the image, all intent So if you click on the white pixel, it selects all the others which are surrounding it and have the same intensity, which here is white. So this means if I select the vent and click inside, I'll get these features. So this means if I click now in my small objects, which I want to get an eye on, how big are they approximately, and then I simply start the measurement. First I go to Analyze Set Measurements, because I need to make sure, as Ari showed beforehand, I need to make sure that everything I want to measure is active, and what we want to measure at the moment is the area of those particles. So Analyze Set Measurements, and the area at least should be active. Or you can directly also add the mean gray value now, and yeah, should be sufficient. So this means if I now have the selection around my particle and I go to Analyze Measure, or you see the shortcut M is way more convenient. So then you get the results table, and the first column is in this case area, so this is what we want to get an idea about. So I click in a few of the bigger ones here and press always M. And then to compare it, I can also measure a few of the bigger ones, and then you quickly see that in this case easy to separate, because the small ones are all smaller 100 pixels and the other ones way bigger than 1000. So if we choose a cutoff value in between of an area of 500 pixels, no problem. This is not always that easy. So you will later on see why we need, or now see why we need that. So we basically use now the tool Ari showed, the Analyze and the Analyze Particles. So and tell the program as measured, everything smaller 500 pixels should be eliminated or excluded from the analyses. We have no upper limit, therefore we keep infinity. The circularity is here not needed because we don't have any kind of elongated features which is helpful to use the circularity for. So here we can keep that at the standard. What we want to get out of that is finally a mask image, which is basically the same as this one with an inverted LUT and showing only the analyzed particles. We will have a look at the summary window. And as mentioned, we want to exclude edge objects because they're not complete. Okay, so 500 to infinity, masks, summary, and exclude objects. If you now run that, then you see you get only those. The small ones are excluded, and the ones which were at the corners are excluded. And in the summary window, it directly tells you at the count 16. That means what we have currently here in the image are 16 of those nuclei which we have counted. So 16 nuclei. Now what we want to know is potentially in average, how many spots in this experiment do we have in average in these nuclei? So then we cannot simply use that image and do the same as we just did and count them, because now these are still included here at the edges, so we would count way too many. So we somehow need to extract here only those spots which are still, or which are existing in only the ones we have extracted, so only our 16 ones. And what we can do therefore is first I will change this inverted LUT. You can do so under image lookup table and invert LUT, and then you see that it's the same as the original. So now how can I get only those spots which are inside these ones? If you go to the green cube and start the binary feature extractor, then you need to choose the objects. So the objects in my case are the small ones because I want to extract those ones. Always the one you want to extract are the objects. So this means I need to select the image which has the name differential extraction speckles. My selector is my analyzed image, my mask image, so mask differential extraction nuclei. And then normally I want to have all those spots which are touching those ones basically. So, or which are completely inside, so basically which are covered by this one. So I could use 100%, but since the extraction of those ones might not be perfect and some of the spots might have a pixel outside, then I go a little bit lower, that I'm sure that I have everything which is inside. This was a little bit confusing, sorry. So basically if you have a particle which is lying at the corner here and this corner is not extracted perfectly, then it's not completely inside, but you want to count it. So I'm going here not to 100%, otherwise I would exclude that. And we can have a look at the count output. So if I now press OK, I'll get, you see that here? I'll get now only those speckles from that image which are inside these ones. Okay? And I get the results table which tells me my original objects. So these ones were around 400, were exactly 458. I had 16 selectors, we have seen that already beforehand, and now I have 306 extracted. So basically I directly have my average. I know I have, if I divide the 306 by 16, I have my average number of spots per my nuclei. This is one option, how you could use that. But you need to first extract it with the analyzed particles and then also extract objects from here with this one, but this is how you could use the binary feature extract. So we can close now these extracted images and still keep the very originals, because now I show you an option which does that in one step with different output options. So, and this is the so-called, so if you have again those two original ones, and this is under the green cube, the so-called speckle inspector. It's not only for those kind of images. As soon as you have small objects contained in big objects, you can actually use that. So that looks in the first glance a little bit overwhelming, but it's not so complicated as it looks. So first of all, you need to tell the program the image where are my big objects and where are my small objects. So my big objects are my nuclei, so that is what I choose here. And my small objects are my speckles. So the object size is exactly what I've keyed in for the analyzed particles beforehand. 500 was my minimum cutoff, and I have no maximum cutoff size, so I keep that here as at 999. One day, if I have time, I'll change that to infinity. So object circularity, as beforehand, we don't use that here. And to this function, we come directly after the first trial. The minimum size of the speckles, because also here you might have things which you want to exclude by size from the small ones. This is basically what you would do here. But here, every of those spots really corresponds to a spot in the original image, so we don't exclude here, but you could do so. So now we simply, and we exclude edge objects here, that's important. So now we simply run that, and you see what you get out first. In the first place, you should, at least you should get that. If somebody doesn't get that, then tell me, I need to fix that. So what you get is the color-coded objects. White means excluded, magenta means analyzed, and you see the first number is the number of the object, so they're just consecutively numbered, object 1, 2, 3, 4, 5, and so on. And the second number in the bracket is the amount of small objects contained inside. So this is the basic principle. But we want to have more than that, because you need some Excel tables for your statistics or so. So basically, we cannot only use that image. So this means we run that again. Green cube speckle inspector. Identify nuclei as big objects, speckles as small. Our 500 exclusion size So now to that settings, the speckle number. It might be the case that you have an experiment where your control experiment has always a basal number of small objects and you want to show that separate. So if in your treated sample you have a similar number or a lower number than in your control, you might want to that this is indicated in that image. So here, just arbitrarily chosen, I'll choose here, if I get here an object which has less than 10, it should indicate that. And if it has more than 20, it should also indicate that. And you will see how that looks like. So we again exclude the edges, and then we simply, activate all four options here that you see what is the maximum outcome you can get. So if you now press OK, you get 4 or 5 different things. First of all, the color-coded map, like before. White is excluded. The magenta were the ones which were analyzed inside the parameters. Now you have green and blue. Why? Because the blue means this has less particles than my 10, which I keyed in. So here are my parameter settings. I said speckle numbers, if there are less than 10, indicate that, and more than 20, and the green ones have more than 20. So this is visually separated. I have, in addition, the speckle number list, a speckle list that is nothing else than simply this in numbers. So here is the object number, which corresponds to the first one, and the number of speckles, which corresponds to that column. Here is average statistics, so as we had before, 16 and 306. The average of that, and then separated by color, so the magenta ones, the blue ones, and the green ones. We have also, if necessary, an individual analysis list of the speckles, so of only the small objects. So you see, in my first object, I actually had 17 small objects. So if I go to my list here, then you see the 17 first ones have here the number 1, then comes the number 2. So these belong to object number 1 and have the standard output for the analyzed particles, so all things you can analyze. And I have the ROI manager with the object numbers, which has the advantage that I can again check how did my ROI look like. And I can go in a second step to my original image, do a background subtraction, normal noise subtraction, and actually use that to transfer all the ROIs I have here for the objects of interest, and can then do an intensity measurement by basically simply go to measure and have a look at the column which has the heading mean, which is the average intensity, which is normally the standard value we use to compare these objects to each other. So you don't need to sit down and make manual ROIs. You can use either the speckle inspector if you have 2 different image types, or analyze particles, because analyze particles on one binary image only, analyze particles has also this option, add to manager would do exactly the same, so it would read in the outlines of all analyzed objects. So much for this differential analyses here. Yeah, so this is what you've seen, what you can get out from that. So you've seen the particle analyzer, and what goes simple always goes more complicated. So we have here an extended particle analyzer, which is very similar but uses a lot more parameters, but also has the option that you can analyze or separate things by exactly their shape, for example, because it uses a lot of shape descriptors, as you see here. So for example, circularity, which is also in the normal analyzer, and roundness, solidity, compactness, and so on. So this image is also online on the Fiji homepage if you need to have a look at that to see which parameter to extract. The rest is actually exactly the same. The problem is now just how can I identify the parameter or the parameter combination which is helpful for me. And that, by trial and error, would take years here. So there is the possibility also in the toolbox that you can use the so-called shape descriptor maps. We'll directly do that on an example. And in the shape descriptor maps, you would get, actually you don't get a montage, you get it as a stack, but you get your particles color-coded according to a specific LUT you choose, which show the different shape descriptors or sizes or so in color. And then you see white is big and blue is small. So you can visually already separate them better, and then also get, if you click on those images, you can get these plots, which is simply a distribution, a cumulative distribution of those sizes or shapes. And then if you want to find a specific cutoff value, you can click in those plots, which are the standard image J plots, on list, and you will get the list where these shapes or whatever sizes are listed. I can show you that then. And then basically use, if you figure out, okay, there is a jump or here is a jump in the plot, so this might be a possibility where I can cut off things. So for example here, for example 9 is the solidity, and you see all the roundish ones have a higher solidity than rather those ones which have a cavity. So I can use the solidity to basically separate them from each other. And if I can find a good value here, then I can use that, key that in here, and get the analyses. So this is one thing we still test here. In exercise 6. An artificial image, but shows you different shapes and how we can separate them. Size might be difficult because even the different shapes might have a similar size. So basically, how can we do that? So if you take that image and then go to the green cube and choose shape descriptor maps, you need to tell the program if you have white or black particles. You see the standard functions you have in addition, water shedding, filling holes, and so on. We need a calibration bar somehow to later on be able to identify the things, if something is big or small. And you can enable this interactive plots. This is what we keep active at the moment. Here is a message, because this is still at the moment a macro, because it keeps later on a mouse listener active and checks if you click on such an image. And if you are done with that, you should press OK, because otherwise it's continuing checking that. But latest, if you close the stack, then it's abolished. So if you now press OK, it takes a little bit. The more particles you have, the longer it takes. So you get this calibration bar. And then you get the original image first. If you have chosen close holes or so, fill holes, then you would have these ones filled here. And then if you go through, then you get these color-coded ones. So here you see up always in brackets what this is. This is now the area, and it's clear that this one is the biggest one, so we can basically identify them and separate them potentially here. If we go further, parameter, then we see we could easily extract those 3 ones or those 2 ones by using parameter as an option. Ferret's diameter, or for example the circularity, you see they vanish completely, so a low circularity would help. So how can we get these values? Show you that for a few ones. If we, for example, want to get only those rectangular ones, and here in the aspect ratio part they have a higher value than the other ones. So if I click mostly a little bit longer inside, then I'll get a plot. And I can do that for other ones as well. So I can go here, for example, to solidity, click inside, get the plot for solidity, and potentially for extent. Where in extent you see that those 3 ones, or potentially in addition to that, have a high solidity. So first of all, now I press escape and cancel that thing here, then I get the results table. Oops. No, doesn't do that. Okay. And then I'll have a look at that. If I want to use the aspect ratio, for example, I could normally extract those 3 ones. So if I click here on list, you see most of the objects actually have a very low aspect ratio because they're not elongated. Those ones have a higher one. So if we go down to in the list at the end, then we see here, okay, we have here a fairly high aspect ratio. So we could use anything above, for example, 3 or 4, and we should be able to extract them. We can test that. So I can go to my original one, then go to the green cube and run the extended particle analyzer. Then I'll search for the aspect ratio, and we said here that, yeah, like something around 5, between 3 and 7. So if I use here the aspect ratio of 5 to infinity, as an output option, I want to have the masks again. I don't want to see my results now, just to show you what you can extract. And I want to reset the whole settings here because it remembers what you key in here, and that might later on be troublesome. So you can also afterwards reset that to the default values, reset this here. So now if I press OK, then you see, get my result. So then you see that I extracted only those 3 ones where I got the parameters for. And the same I could do now, for example, for whatever. What else have we chosen here? Extent is the same. So for example, for the solidity, so if I go in that stack to solidity, then in solidity you see, actually I don't know if you see that in front, these lines we had here are very dark, they are shown in blue. The other ones are brighter, so they have a bigger solidity. So if I go to my list, here is basically the jump which occurs. So I have here a very low solidity, and then I get higher ones. So if I stay below 0.1, I should be able to extract them. So I can go to my original, start green cube extended particle analyzer, then go to the solidity, and we said if we stay below 0.1, then we get exactly those lines. So this is the one we would extract, and if you would have results table active, then you would also get the results for those ones. So this is how you can use a combination of the shape descriptor maps and the extended particle analyzers to specify it specifically to specific shapes, for example. So, few things. Just to mention that also here, because if we have particles extracted, we might be interested in if they are clustering, for example, or not. In general, we can have first an estimation in the image. Is there a clustering occurring or not? That is done by a statistical comparison of the distances between the particles. Therefore, we have here the 2D particle distribution. And here it is fairly obvious that we have somehow a clustering in some areas in comparison to other areas. So you see here we have the same options, exclude first of all things, and then we can do the comparison by either the mean distance or the median distance. So if you use the mean distance, you need to be careful, because otherwise if you have a lot of outliers, they're included and mess up the results. So if you have a lot of outliers, the median would be better. Otherwise, mean is fine, and you can choose a certain confidence interval with which you want to analyze that. And according to that, the analysis of the particles is run. There is the estimated distance between the particles which should be there and the one we measure, and according to that they are compared, and according to that it will tell you you have clustered particles with a certain p-value according to the choice of your confidence interval. Or so the 3 options are either you have clustering, or you have a random distribution, or you have a self-avoiding distribution where all of them have basically almost the same distance. So these are options for that one. I think time-wise we're not going through that. If you're interested in that, we can also add the poster later on or talk after lunch or in lunch break for those ones, because connected to that, there is also a possibility to then indicate where are these clusters occurring. That is never no question that is user biased, because you need to key in a size of a tool which should check for the clusters. These are these small circles. And for a density, in this case, the density means you have a certain density in your image overall, and in a cluster you have a higher density. So basically, if you key in here 6, that means and you identify only the clusters which are which have a 6-fold higher density than the rest of the image. That would be a possibility here with the size of that circle of 30. You can do it with the centroid nearest neighbor distance. That is applicable if your objects have the same size and are rather roundish. If they are very different in size and are amorphous, then the shape influences the distance between the particles. Then what we would need to use is the average nearest neighbor distance, because then it actually checks what is exactly the distance between the outer shape of the particles. And according to these distances, it does the cluster finding, and you see that you can then indicate the clusters connected or unconnected, and show that in the image. So other functions we have here is, for example, the neighbor analysis. This is a little bit similar. So you can indicate in a binary image, if you have such a image, for example, how many neighbors does each particle have. There are many different options. You can do that by either the neighbors according to the Voronoi diagram, so basically really how many neighbors are there, or you can specify a distance. You can tell the program, okay, in a distance of 50 pixels around each particle, how many neighbors are there? And that is then shown in color with the calibration bar, and it shows you the distribution. So here you clearly see that most of the particles have 5 neighbors and 4 neighbors, and then the neighbor distribution drops. So this is a possibility if you click on neighbor analysis. You have some plots. I need to update that because of the nice function Wayne mentioned in the morning, that we can now zoom in and zoom out of those plots. That is a little bit affected by that. But basically you have with these plots the chance to put from many images and lines the plots as an overlay to compare them. For example, comparing coincidence in specific areas, that is a possibility. Or you have a stack line plot where you can make any kind of line, freehand line, segmented line, straight line. If you have either a set stack or you have a time stack, then you will plot along that stack, basically along the line, so you see the changes through your volume or the changes over time along that line. So that is a possibility as well. So how is time? So actually, if you have any basic things you want to look up for this toolbox, you can go to the Fiji homepage. There is the bivoxel toolbox available with all the options and short explanations. In general, if you find that something is not working, you find a bug, email me and I'll try to change that. Otherwise, if you have any suggestions, you're welcome to report that, and if I find some free time, I will include that as well. You can have a look at the bivoxel www.bivoxel.de or com homepage with some further information also on the courses in general, and the toolbox here you will also find for ImageJ users the newest versions here to download, and for Fiji users anyway you can use the update site to update that. So, and at this point I don't want to keep you longer from lunch break, so I would like to say thanks to the organizers for having me here. I would like to thank all the users, the input from the users, that is very helpful also for me, and I would like to thank you for your interest. I hope you could take some things with you, and potentially we'll see each other at the poster and can have a lively discussion. Thanks.